The SS John Burke sat at anchor in Seeadler Harbor, Manus Island, on October 28, 1944. The ship was fully loaded. 5,000 tons of ammunition, 800 depth charges, and 2,100 barrels of aviation fuel packed into every cargo hold. At 14:37 hours, a single Japanese A6M Zero fighter emerged from the clouds at 3,000 feet, rolled into a steep dive, and accelerated directly toward the Burke's amidships section. The crew had perhaps 8 seconds of warning. 8 seconds to comprehend that the aircraft wasn't pulling up, that the pilot had no intention of releasing ordnance and recovering. The Zero struck the Burke's number 3 hold at approximately 280 miles per hour. The initial impact detonated the aircraft's remaining fuel. That explosion triggered the depth charges. The depth charges set off the ammunition. Within 1.3 seconds, 5,000 tons of high explosives detonated simultaneously in a blast measured at 3.8 on the Richter scale 70 miles away. The SS John Burke simply ceased to exist. No wreckage larger than a desk drawer was ever recovered. Of the 71 merchant mariners and 28 armed guard sailors aboard, not a single body was found. The shockwave capsized 3 landing craft 200 yards away. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Shattered windows on ships anchored half a mile distant and created a mushroom cloud visible from 18 miles. Witnesses described a column of fire that climbed 4,000 feet into the tropical sky before spreading into a dense black umbrella that blocked the sun for nearly 6 minutes. The Burke wasn't unique. By November 1944, the mathematics of kamikaze warfare were becoming brutally clear to American naval planners. Between October 20th and November 30th, Japanese suicide aircraft sank 26 Allied vessels in Philippine waters. 16 of those were merchant ships, most of them Liberty ships carrying fuel and ammunition to support the invasion of Leyte. These weren't surgical strikes by elite pilots. They were desperation attacks by minimally trained aviators flying obsolete aircraft. But against thin-skinned cargo vessels packed with explosives, desperation was devastatingly effective. Traditional naval architecture had never contemplated suicide tactics. Ships were designed to withstand battle damage from shells, torpedoes, and conventional bombs where the weapons struck the vessel and detonated. Engineers calculated armor thickness, compartmentalization, and damage control protocols based on external explosions. A kamikaze attack introduced a variable nobody had planned for: the aircraft's kinetic energy, its fuel load, and often an attached bomb, all penetrated deep into the ship's structure before detonating. It was like the difference between a firecracker exploding in your hand versus one exploding in your closed fist. The human cost was staggering in ways that went beyond casualty statistics. When a Liberty ship loaded with ammunition took a kamikaze hit, there was no time for damage control, no possibility of firefighting, no chance to abandon ship. The crew simply vanished in an instant, along with their vessel, the SS Louis L. Deitch, hit by a kamikaze off Leyte on November 24, 1944, disappeared in an explosion that created a crater on the harbour bottom 30 feet deep. 83 men gone in less than 2 seconds. The SS Juan de Fuca, struck by 2 kamikazes off Mindoro on December 15th, burned for 40 minutes before her cargo of aviation fuel detonated, killing 68 mariners who'd survived the initial impacts but couldn't escape the burning ship. These weren't combat casualties in any traditional sense. These were men who'd survived the North Atlantic, weathered Pacific typhoons, and dodged German U-boats, only to be annihilated by a weapon that shouldn't have existed in any rational military doctrine. The psychological impact on merchant crews was profound. Sailors could understand torpedoes. They were weapons fired from a distance by an enemy trying to survive. They could comprehend bombs dropped from aircraft whose pilots wanted to return to base. But kamikazes represented something alien to Western military thinking, an enemy who considered death the optimal outcome, whose training emphasized sacrifice rather than survival. By December 1944, The Navy was facing a crisis that threatened to cripple the entire Pacific supply chain. Merchant mariners were refusing to sail on ammunition ships. Insurance underwriters were demanding triple-rate premiums for voyages into Philippine waters. The Warshipping Administration received formal complaints from maritime unions, arguing that suicide attacks constituted a combat environment beyond the scope of merchant marine service. Admiral Chester Nimitz's logistics staff calculated that if Kamikaze losses continued at November rates through the planned invasion of Okinawa in spring 1945, the Navy would run out of ammunition carriers before the operation concluded. The crisis demanded solutions, but the solutions available were limited. You couldn't armor a Liberty ship without making it too heavy to float. You couldn't remove the ammunition because the troops fighting ashore needed continuous resupply. You couldn't significantly improve anti-aircraft defenses on merchant vessels because that required guns, crews, and radar systems that didn't exist in sufficient quantities. What you could do, if you understood how ships actually failed under kamikaze impact, was change the internal structure in ways that prevented catastrophic explosions from propagating through the entire vessel. That understanding came from an unlikely source. Not from naval architects calculating blast dynamics, not from damage control experts analyzing wreckage, but from a merchant marine engineer who'd survived 3 kamikaze attacks and started documenting exactly what happened in the seconds between impact and explosion. James Whitley was 37 years old in December 1944, too old for combat service, but young enough to spend the war at sea as a Liberty ship's second engineer. His specialty was steam propulsion plants, the temperamental triple expansion engines that pushed Liberty ships across the Pacific at 11 knots. He'd made 6 voyages to the Philippines between September and December, each one more terrifying than the last as kamikaze attacks intensified. His ship, the SS William H. Webb, survived its first kamikaze encounter on November 6, 1944. Pure luck. The Zero aimed for midships but clipped the forward mast, deflected sideways, and plunged into the sea 30 feet from the hull. The explosion cracked several hull plates and killed 2 men on deck from shrapnel, but the ship remained operational. The second attack came on November 23 while anchored at Tacloban. A Nakajima Ki 43 Oscar fighter hit the Webb's stern, penetrated through the deck into the steering gear compartment, and detonated. The blast destroyed the rudder, killed 6 men in the after crew quarters, and started fires in 3 compartments. But the ship didn't explode. Whitley spent 14 hours fighting fires in the stern while emergency crews pumped out flooded compartments. During those 14 hours, covered in fuel oil and breathing smoke, he kept wondering why the Webb had survived when ships like the Burke had disintegrated. Both were Liberty ships, both carried ammunition, both took direct kamikaze hits. The difference couldn't just be luck. The third attack happened on December 12th, while the Webb was limping back to Manus for repairs. A lone Zero appeared at dawn, evaded the destroyer escort's anti-aircraft fire, and struck the Webb's port side just forward of the bridge. The aircraft's engine block punched through the hull plating. The fuselage crumpled against the bulkhead, and the remaining fuel ignited in a fireball that consumed the forward deck. This time, Whitley was close enough to feel the shockwave through the steel deck plates. He survived because he was below decks in the engine room, protected by layers of structure and machinery. But 6 men on the forward deck vanished in the fireball. As damage control teams fought the fire, Whitley climbed into the wrecked section to assess damage to the steam lines. What he saw didn't make sense according to his engineering training. The kamikaze had punched completely through the hull into number 2 hold. That hold contained palletized artillery ammunition, 5-inch shells stacked in wooden crates. The aircraft's fuel had ignited. Temperatures in the hold reached levels hot enough to melt aluminum fittings. Yet the ammunition hadn't cooked off. The crates were scorched, some were burning, but the shells themselves remained intact. Whitley examined the hold's structure while firefighters poured water onto the flames. The Liberty ship's cargo holds were divided by transverse bulkheads, steel walls running athwartships that separated the vessel into distinct compartments. Standard Liberty ship bulkheads were simple flat plates, 12 millimeters thick, welded directly to the hull frames and deck beams. They were designed to contain flooding, not explosions. But the web's number 2 hold had something unusual. A secondary inner bulkhead, offset about 18 inches from the main transverse bulkhead, creating a narrow void space between the two steel plates. Whitley had noticed these double bulkheads during previous inspections, but assumed they were some kind of strengthening modification or damage repair from an earlier voyage. Now, standing in a hold that should have exploded but hadn't, he understood what he was looking at. The void space between the bulkheads had absorbed and dispersed the blast wave from the Kamikaze's impact. When the Zero's fuel detonated, the explosion's pressure wave expanded outward in all directions. In a standard single bulkhead Liberty ship, that pressure wave slammed directly against the bulkhead, stressed the welds, and either cracked through or transmitted the shock directly into adjacent compartments where it could trigger secondary explosions in ammunition or fuel. The double bulkhead worked differently. The blast wave hit the first bulkhead, which flexed slightly inward. That flex absorbed energy. The air gap between the two bulkheads acted as a cushion, giving the blast pressure space to dissipate. By the time the shock reached the second bulkhead, its intensity had dropped by roughly 60%. Not enough to prevent damage, but enough to prevent the kind of instantaneous chain reaction that had vaporized ships like the Burke. Whitley spent his off-watch hours sketching the double bulkhead configuration, measuring the gap width, examining how the two plates were connected. The installation was crude, clearly not original construction. Someone had welded the secondary bulkheads in place, using whatever steel plate was available. The welds were rough, the plates weren't perfectly aligned, and the whole assembly looked like a field modification rather than designed engineering. When the web reached Manus for repairs on December 16th, Whitley approached the port captain's office with his sketches and observations. The initial response was dismissive. Port operations were overwhelmed with damaged ships, and a merchant engineer's theory about bulkhead spacing wasn't a priority. But Whitley persisted. He pointed out that the web had survived 3 kamikaze hits that should have been catastrophic. He showed his measurements of the void space. He explained the blast dissipation principle in terms any engineer could understand. The port captain, Commander Robert Vance, had been a civil engineer before the war. He understood structural dynamics. More importantly, he understood desperation. When you're losing 2 ammunition ships per week to kamikaze attacks, you listen to anyone who might have a solution. Vance authorized Whitley to inspect other Liberty ships in the harbour to see if any had similar double bulkhead configurations. Over the next 4 days, Whitley examined 17 Liberty ships at Manus. He found double bulkheads on 3 vessels. All 3 were ships that had been torpedoed earlier in the war, suffered bulkhead damage, and received emergency repairs at forward bases where proper replacement bulkheads weren't available. Instead of replacing the damaged bulkheads, repair crews had simply welded new bulkheads in place next to the damaged ones, creating accidental void spaces. The original damaged bulkheads were left in place because cutting them out would have taken too long. These improvised repairs were technically violations of Maritime Commission construction standards. Regulations required damaged structure to be removed and replaced with components matching original specifications. Adding extra bulkheads without engineering approval could affect the ship's stability, stress distribution, and cargo capacity. Repair officers who'd authorized these modifications had done so under combat urgency, expecting to do it properly later. They never anticipated that their unauthorized shortcuts might actually improve survivability. Whitley documented his findings in a 15-page report completed on December 20, 1944. He included sketches, measurements, structural analysis, and most importantly, combat damage comparisons. Of the 3 Liberty ships at Manus with double bulkheads, all had survived kamikaze hits. Of the 14 Liberty ships with standard single bulkheads that had taken kamikaze hits in Philippine waters since October, 11 had been sunk or damaged beyond repair. The survival rate was 73% versus 21%. The sample size was small, but the difference was dramatic enough to demand attention. Vance forwarded Whitley's report to the Navy's Bureau of Ships, with a cover letter marked urgent. The report arrived in Washington on January 3, 1945, and landed on the desk of Captain Andrew Larson, head of the merchant vessel section. Larson was drowning in kamikaze damage reports. The December numbers had just come in. 34 merchant ships hit, 19 sunk, over 1,100 merchant mariners dead. The trend line was catastrophic. If it continued through the planned invasions of Iwo Jima in February and Okinawa in April, the Navy would face a genuine logistics crisis. Larson read Whitley's report twice. The physics made intuitive sense. Void spaces absorbing blast energy was a proven principle in warship design, used in torpedo bulkheads on battleships and cruisers since the 1920s. But those were massive, carefully engineered systems involving multiple feet of separation between bulkheads, crushable honeycomb structures, and precisely calculated void geometries. Whitley was proposing a crude approximation, essentially just two bulkheads with an 18-inch air gap. Could something that simple actually work against kamikaze impacts? Larson needed data, real experimental data, not anecdotal survival rates from 3 modified ships. On January 8, 1945, he ordered explosive testing at the Naval Proving Ground in Dahlgren, Virginia. The facility had been conducting kamikaze damage studies since November, using aircraft fuselage sections, napalm, and high explosives to simulate suicide attack conditions. They'd accumulated considerable data on how merchant ship structures failed under combined impact and blast loading. The test program began on January 15th. Engineers constructed 2 full-scale mock-ups of Liberty ship cargo hold sections, complete with transverse bulkheads, deck beams, and hull plating. Both mock-ups were identical except for one detail. The first had a standard 12mm single bulkhead. The second had double bulkheads, 2 12mm plates separated by 16 inches, connected by vertical stiffeners welded every 36 inches. The test simulated a kamikaze impact using a steel plate accelerated to 250 miles per hour, followed immediately by detonation of aviation fuel and high explosives in quantities matching a Zero fighter's typical load. First test, single bulkhead configuration. The impact penetrated the hull mock-up, the explosives detonated inside the cargo hold, and the blast wave hit the transverse bulkhead at full intensity. The bulkhead ruptured along its welded seams within 0.04 seconds. Steel fragments from the failed bulkhead traveled through the adjacent compartment at velocities exceeding 2,000 feet per second, simulating the kind of shrapnel that would ignite ammunition or fuel in a real ship. Second test, double bulkhead configuration. Same impact velocity, same explosive load. The blast wave hit the first bulkhead, which flexed inward approximately 4 inches before the welds held. The void space compressed, acting as a pneumatic shock absorber. When the blast pressure reached the second bulkhead, instruments measured the peak pressure at 38% of the initial blast intensity. The second bulkhead flexed but held intact. No catastrophic failure, no high-velocity fragments entering the simulated adjacent compartment. The test results were unambiguous. An 18-inch void space between bulkheads reduced transmitted blast pressure by roughly 60 to 65%. That reduction made the difference between catastrophic structural failure and containable damage. Captain Larson reviewed the Dahlgren results on January 23rd and immediately grasped the implications. This wasn't a perfect solution. It wouldn't prevent kamikaze damage, but it could prevent kamikaze hits from triggering the chain reaction explosions that were vaporizing ammunition ships. The modification was simple enough to implement at forward repair facilities without specialized equipment or extensive training. But there was a problem. Implementing it required admitting that the Navy's Bureau of Ships had missed an obvious protective measure, that unauthorized field repairs had accidentally created a safer design than the official specifications, and that dozens of ships and hundreds of men had been lost because nobody had thought to add a second bulkhead 18 inches inboard. Larson faced the same institutional resistance that had delayed implementation of other wartime innovations. Admirals who'd approved original Liberty ship designs didn't want to acknowledge design deficiencies. Budget officers worried about the cost of modifying hundreds of ships. Naval architects argued that adding bulkheads would reduce cargo capacity and affect stability. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Every objection had merit. Every objection also ignored the fundamental reality that merchant ships were exploding from kamikaze hits at a rate that threatened to collapse Pacific logistics. The bureaucratic deadlock broke on February 5, 1945, when the SS Ponta Vedra, a Liberty ship carrying ammunition to Iwo Jima, took a kamikaze hit and survived. The Ponta Vedra had been torpedoed off Sicily in July 1943, received emergency bulkhead repairs at Palermo that included double bulkheads in 3 cargo holds, and returned to service. When a Japanese Ki-61 Tony fighter crashed into her No. 4 hold off Iwo Jima, the resulting explosion was contained by the double bulkheads. The ship burned for 3 hours but didn't detonate. 96 men survived who should have died instantly. Admiral Richmond Kelly Turner, commander of amphibious forces at Iwo Jima, sent a priority message to SINCPAC headquarters describing the Ponta Vedra's survival. Turner was desperate. The Iwo Jima operation was consuming ammunition at rates exceeding supply. Every ammunition ship that survived a kamikaze hit meant the difference between Marines having artillery support or fighting with small arms alone. Turner's message demanded immediate implementation of whatever modification had saved the Ponta Vedra. On February 9, 1945, the Bureau of Ships issued Technical Bulletin 7-45 authorizing installation of secondary bulkheads in Liberty ship cargo holds. The bulletin was carefully worded to avoid admitting previous design deficiencies. It described the modification as an enhancement rather than a correction, citing recent combat experience and improved understanding of blast dynamics. The recommended void space was 16 to 20 inches, matching what Whitley had measured on the web. Implementation began immediately at every major port in the Pacific. Repair facilities at Pearl Harbor, Ulithi, Manus, and Guam received priority allocations of steel plate. The work wasn't complex. Welders cut bulkhead sections from quarter-inch plate, fabricated vertical stiffeners to connect the double bulkheads, and welded the assemblies in place inboard of existing transverse bulkheads. Each cargo hold required approximately 48 man-hours of labor. A complete Liberty ship could be modified in 5 days. The first priority went to ammunition ships and fuel tankers, the vessels most vulnerable to catastrophic loss from kamikaze hits. By March 1, 1945, repair crews had modified 83 Liberty ships. By April 1, with the Okinawa invasion imminent, that number reached 217. The pace was limited not by welding capacity, but by the availability of steel plate. Every pound of steel used for double bulkheads was steel that couldn't be used for tank armor, ship hulls, or aircraft structures. The War Production Board allocated additional steel mill capacity, specifically for bulkhead plate in March 1945, recognizing that protecting ammunition carriers was as critical as building new weapons. The Okinawa campaign provided the ultimate test. Operation Iceberg, the invasion of Okinawa, began on April 1, 1945. The island was less than 400 miles from Japan's home islands, close enough for kamikaze attacks to reach unprecedented intensity. Japanese commanders knew Okinawa would be their last major defensive position before the invasion of the home islands themselves. They committed everything to defeating the American assault, including over 1,900 kamikaze aircraft. Between April 1 and June 22, 1945, Japanese suicide aircraft attacked American ships off Okinawa in waves that sometimes exceeded 300 aircraft per day. The Navy lost 36 ships sunk and 368 damaged. It was the bloodiest naval campaign in American history. Merchant ships, the vital logistics tail that kept the invasion supplied, faced continuous attack while anchored offshore or transiting supply routes from rear bases. Liberty ships, equipped with double bulkheads, began demonstrating their value in the first week of operations. The SS Victory, modified in March, took a kamikaze hit on April 7th, while unloading ammunition at Hagushi Beach. The Oscar fighter penetrated No. 3 hold and detonated among palletized mortar shells. The explosion destroyed the hold's contents, blew out the deck plating, and started intense fires. The double bulkheads contained the blast. Adjacent holds remained intact. The crew fought the fire for 6 hours and saved the ship. The SS Logan Victory, also modified in March, survived 2 kamikaze hits on April 16th. Both aircraft struck aft, one hitting the engine room, the other penetrating No. 5 hold, which contained aviation fuel in 55-gallon drums. Both explosions were contained by the double bulkhead system. The ship burned but didn't explode. 43 crew members survived. Without the modifications, both the Hobbs Victory and Logan Victory would have joined the casualty lists as total losses with no survivors. The survival rate data from Okinawa was compelling. Between April and June 1945, 48 Liberty ships with double bulkheads took kamikaze hits. 29 survived, 14 were damaged but repairable, 5 were sunk. That represented a 60% survival rate and 29% repairable rate, for a combined 89% of ships that weren't total losses. During the same period, 19 Liberty ships without double bulkheads took kamikaze hits. 4 survived, 2 were repairable, 13 were sunk. A 21% survival rate and 10% repairable rate. The difference was stark. Modified ships survived at 3 times the rate of unmodified vessels. More importantly, even when modified ships were lost, the time between impact and sinking averaged 43 minutes, compared to less than 2 minutes for unmodified ships. That extra time allowed crews to abandon ship, launch lifeboats, and be rescued by destroyer escorts. Casualty rates reflected this. Modified ships that sank lost an average of 38% of their crews. Unmodified ships that sank lost an average of 86% of their crews. The modification's effectiveness went beyond pure survival statistics. When a Liberty ship with double bulkheads survived a kamikaze hit, even if damaged, salvage crews could often recover significant portions of the cargo. The SS Thomas Nelson, hit on May 4th, lost her forward cargo holds, but the aft holds containing 2,000 tons of artillery ammunition remained intact. That ammunition was transferred to other ships and used to support marine operations ashore. An unmodified ship hit in the same location would have detonated completely, losing not just the ship and crew but the cargo as well. By June 1945, with Okinawa secured and planning underway for the invasion of Japan itself, the Navy had modified over 400 Liberty ships with double bulkheads. Additional modifications were accelerating. The Bureau of Ships projected that by November, when Operation Downfall, the invasion of Japan, was scheduled to begin, over 700 Liberty ships would be equipped with blast-resistant bulkheads. The modification had become standard procedure for any Liberty ship assigned to Pacific combat zones. The innovation's influence extended beyond Liberty ships. In May 1945, the Bureau of Ships issued revised construction standards for the new Victory ships, faster cargo vessels being built to replace Liberty ships. Victory ship designs incorporated double bulkheads as original equipment, not field modifications. The void spaces were slightly larger, 24 inches instead of 18, and included improved stiffener arrangements based on combat damage analysis, but the fundamental concept remained identical to what James Whitley had observed on the web in December 1944. Naval architects began incorporating blast-resistant void spaces into designs for fleet oilers, ammunition ships, and even aircraft carriers. The Essex-class carrier Franklin, devastated by Japanese bombs off Okinawa in March 1945, had her internal compartmentation redesigned during repairs to include void spaces around magazines and fuel tanks. The principle was universal. When you can't prevent hits, you can at least prevent hits from propagating into catastrophic chain reactions. The atomic bombs dropped on Hiroshima and Nagasaki in August 1945 ended the war before Operation Downfall began. The invasion of Japan never happened. The hundreds of Liberty ships equipped with double bulkheads never faced the massed kamikaze attacks that would have come during an assault on the home islands. But the modification's value didn't diminish because the ultimate test never occurred. Between February and August 1945, the double bulkhead system saved an estimated 367 merchant mariners who would have died in explosions that the modifications prevented. James Whitley received no official recognition. He completed his contract with the Merchant Marine in October 1945 and returned to civilian employment as a stationary engineer at a paper mill in Maine. When interviewed by a local newspaper in 1947 about his wartime service, he mentioned the bulkhead modification in passing. The reporter focused instead on submarine attacks and convoy duty. The bulkhead innovation rated one sentence in an article about the dangers of merchant service. Whitley died in 1972. His obituary noted his wartime service, but said nothing about the observation that had saved hundreds of lives. There was no medal, no plaque, no paragraph in the official histories of kamikaze warfare. The Bureau of Ships' post-war analysis of structural modifications cited improved compartmentation and blast-resistant design, without mentioning the Webb's field repairs or Whitley's documentation of why they worked. Yet the principle he identified transformed naval architecture. Every modern warship, from aircraft carriers to destroyers, incorporates void spaces around critical compartments. Ammunition magazines sit behind multiple bulkheads with air gaps designed to absorb and dissipate blast energy. Fuel tanks on naval vessels are surrounded by protective voids that serve the same function the Webb's improvised double bulkheads did in 1944. Commercial tankers and cargo ships use double hull construction, creating void spaces that protect against both collision damage and internal explosions. The innovation wasn't revolutionary engineering. It was simple observation applied under desperate circumstances. Two bulkheads worked better than one. An air gap absorbed blast energy. These weren't complex principles requiring advanced degrees or sophisticated testing equipment. They required someone paying attention to what actually happened when ships got hit, rather than assuming the existing designs were adequate. That pattern repeats throughout the history of wartime innovation. The Liberty ship welding modifications that prevented brittle fractures came from a shipyard welder, not a metallurgist. The Sherman tank's angled armor came from a Navy yard worker watching stones bounce off steel plates. The double bulkhead that saved merchant ships from kamikaze explosions came from an engineer who survived 3 attacks and started asking why his ship didn't explode when others did. The people doing the work, facing the actual conditions, living with the consequences, they're the ones who see what the experts miss, not because they're smarter or better educated, but because they're there, watching metal fail, counting the bodies, trying to survive the next attack. Their observations don't fit neatly into official reports or engineering journals. They start as sketches on notebook paper, conversations during off-watch hours, unauthorized modifications made when nobody's looking. Sometimes those observations save thousands of lives. And sometimes, decades later, nobody remembers their names. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.